Right. So exponential functions are different from what we've been doing in the sense that until now, we have had polynomial functions where you basically had, a variable to the power of, a number, right? Like x to the power of 2, y to the power of 4, and so on. But now we have exponential functions where you have a number to the power of x. Okay, so b to the power of x. And b is the base, which is just a constant, right? So, for example, right, y equals 3 to the power of x, right? Do you see how this is different from, let's say, x squared, where x was the base? Now the number is the base, and the exponent is the number. Okay, or the variable. Okay, so, 1 second. All right. So first off, we're going to talk about what the graph of these things look like. The graph of an exponential function has an asymptote. An asymptote is an imaginary line that the graph comes really, really close to but never touches. Okay? So it comes really, really close to but never really touches. So so let's first start by talking about exponential growth. Now, when you have the equation, how do you know if it's exponential growth? The equation looks like this, and that number b has to be greater than 1. That's what makes it growth. All right? Now, this is what's important. For the domain of all exponential functions is all reals. So there is no thinking involved. The domain for all exponential functions is all reals. The range has to do with the asymptote. So for example, whatever the asymptote is, right, the range is going to be either y is greater than the value of the asymptote or y is less than the value of the asymptote. In the default case, the asymptote is y equals 0. So for the range, it's either going to be y is greater than 0 or y is less than 0. Okay, how do we know? When you have the graph like this above the asymptote, then the range is y is greater than 0. If it's below, then it's got to be less than. So let's talk about that asymptote for a minute. That asymptote in here, the default case is y equals 0. We always draw it with with a dotted line because it's an imaginary line. You cannot draw an exponential function without the asymptote. So if I were to ask you to draw a bunny rabbit, right? You could be the worst artist in the world, but what is the one thing you put on there to know for people to know that it's a bunny rabbit and not like, I don't know, the ears, right? Because you can't draw a rabbit without the ears. You can't draw an exponential function without the asymptote. Then it's not an exponential function. Okay? All right. So let's talk about exponential growth then. So let me give you a little bit of an example. Actually, this week, this is the perfect example, right? So you come to school on a Monday morning, you're feeling fine, and oh my God, I haven't seen you in like 48 hours. Oh my God, my life was going to end without you. So like, you're hugging and, giving all your friends a hug. And then your friend's like, oh, I feel sick. And so you are fine in the morning, right? But then by like bonus, you're just like, oh my God, I just, something here. And then by lunch, you're just not feeling well. You go home. That evening, you are just done. So what happened? You had little to no viruses or bacteria in you. Your friend did. When you went in to give them a hug, they coughed all over you. So now a little bit of bacteria went into your body, and then it multiplied and multiplied and multiplied and multiplied, and by lunch, you were done. So that's how rapidly it multiplied. That is exponential growth. The big thing about exponential functions is how rapidly they change, right? So if I were to take one x value here and another x value close by, look at how little I went over in the x's, but look at what a big difference that made in the y's, right? That's an exponential function. Now, this is exponential growth because as time went by, the quantity increased rapidly. So the big thing about exponential growth is as x approaches infinity, the graph moves away from the asymptote. All right? Okay. So, how are we going to graph these? Here we go. We're going to graph a very simple case, 2 to the power of x using a table of values. This is exponential growth because this number b, that number is greater than 1, so it's exponential growth. Okay, for exponential growth, I like to pick these numbers to plug in. This is not, written down like as a law anywhere, but these are just, they lend themselves to good problems. Okay, so 2 to the power of minus 1 is 1 over 2, so that's a half. 2 to the power of 0 is 1. Now, when you have x equals 0, that is your y-intercept, right? So the y-intercept is 0, 1. Next, 2 to the 1 is 2. 2 to the 2 is 4. Okay, so let's go down here. The asymptote is y equals 0. The y-intercept we just said was 0, 1. Okay, let's go ahead and start graphing this. I put down the asymptote first. If your asymptote falls on the x-axis, you have to make it visible. So it's okay to go like a hairline above to make it visible. Okay? Just a tad bit above. All right. So now let's go ahead and graph this. So at negative 1, we're at a half, then 1, then 2, then quickly to 4. Now, when you graph this, this is not okay because this is not connect the dots in kindergarten. You really have to show that this follows the asymptote on this side and this increases rapidly on that side. Now, that is a beautiful exponential function, okay? Okay, the domain for all exponential functions is all real numbers. There is zero thinking involved there. So the range, it's always going to be compared to the asymptote, which is 0. If it sits above, then it's greater than 0. All right? Okay, how about exponential decay, right? Exponential decay. So suppose, you do get sick, your friend really made you sick. And then you end up going to the doctor. Yep, it's a bacterial infection. They give you antibiotics. You take 1, you take 2, and all of a sudden, oh my God, I'm feeling so much better, right? Because the antibiotics killed the bacteria very, very quickly. Now, again, there is an asymptote here. So over time, the amount of bacteria pretty much all died, right? But does the antibiotics ever kill every last cell of bacteria? No. So you see how even in real life, it comes very, very close to 0, but never really hits 0. That's the asymptote. Okay? All right. So we know that a function is exponential decay when that value of b is between 0 and 1. Okay, so like a fraction less than 1, between 0 and 1. Okay, this is how the graph looks. So as x approaches infinity, the graph moves toward the x-axis, the asymptote, sorry. Okay? Again, the domain is all real numbers, and then everything else is the same. All right. So now let's graph this one. Y equals 1/2 x. Do you see how this is a exponential decay? Because the half is less than 1, right? It's between 0 and 1. So again, we're going to use the same values here. So let's see. -1. So this is going to be half to the power of -1. This is 2. Okay. Half to the 0, that's 1. Again, that's the y-intercept. Half to the 1 is 1/2. Half to the 2 is how much? 1/4. Okay, so asymptote. Before I graph this, let's go down here. The asymptote is y equals 0. What's the y-intercept? 0, 1. What's the domain? All real numbers. Okay, and the range, again, it's going to be compared to 0. Now, you shouldn't have to wait for the graph to figure out the range. Take a look here. The A value, right, the coefficient of this 1/2 is a positive 1, right? If it's positive, it's going to go above, so it's got to be greater than 0. If you do greater than or equal to, it's points off. It can never be 0. Okay, so at -1, we're at -2. Sorry, at -1, we're at 2. Then 1, then half, then a 4th. Okay, so do you see how, like we went from a half to a 4th? If this was a 3, 1/3, it would have been 1/3, 1/9, and that's just silly. So usually for decay, usually for exponential decay, I like to go like -2, -1, 0, 1. It makes the numbers a little bit more manageable. Okay? All right. Okay, transformation. So let's talk about transformation. So remember, the parent function is b to the x. So the transformations will look like this. You can have a times b to the x minus h. So h is a horizontal translation, right? And k is a vertical translation. A is the vertical stretch or compression, right? If it's greater than 1 or less than 1. And also, if A is less than 0, then this is a reflection around the x-axis. Okay? All right. So take a look at this one. This one has a translation downward 2 units. Okay, if the graph moves down, everything moves down, including the asymptote. So where is the new horizontal asymptote now? Okay, the horizontal asymptote always has to be written as y equals a number. Y equals a number. Okay, never, if you write -2, it'll always be -1. Okay, so y equals -2. Good. So now, is this a growth or decay? Growth. Okay, by the way, what's the domain? All real numbers. And what's the range? So we're going to compare it to -2 because that's what the asymptote is, greater than -2. Okay, since it's growth, I'm going to pick -1, 0, and 1. So 2 to the -1, -2. 1/2 -2, -3/2. 0, that's the y-intercept, is 1, -2, -1. And then 2 to the 1 -2, that's 0. Okay, let's go. Oh, hi. Okay, asymptote time. You see how I do that first? Then I put in my points. So at -1, I'm at -1.5. And then -1. And then 0. Go up. go this way. This was exponential growth. Does this look like exponential growth? Yes, because it's moving away from the x-axis as x approaches infinity. All right? Yeah.
How do you know what points to pick?
So if it's exponential growth, always go with -1, 0, 1, and maybe 2. If it's exponential decay, go -2, -1, 0, 1. Yeah. Anything to the power of 0 is 1. It's the rules. No.
No, wait, sorry, that's what I meant.
Okay, I'll tell you why. I'll tell you why. So if you have 2 to the 3 over 2 to the 3, okay, let's do that. We learned last chapter that this, okay, what is that? How much is that? 1. But we learned last chapter that this is also 2 to the power of 3 minus 3, right? Because you subtract the exponents. So that's 2 to the 0, which is also 1. Right? Yeah. Okay. That's more of an, okay. So, okay. What's the horizontal asymptote here? Y equals -2. Okay. Yeah. Okay. So domain, all real numbers. What's the range? Yup. Okay. So this is again growth. So I'm going to pick -1, 0, 1. So now look, there is also a horizontal translation. Where has this graph moved? Left or right? Left, right. I mean, left, correct. Yes. Okay. So 3 to the power of -1 plus 1 minus 2. This is 3 to the power of 0 minus 2, which is what these days? -1. 3 to the power of 1 minus 2. 1. 3 to the power of because it's 0 plus 1. Okay, I first put my asymptote in. So I get, oh my God, come on now. The asymptote? Oh my God, yes. I thought we went over this. Like a bunny without the ears. Who would know? Who would know? Who would know it was a bunny? It could be any other animal. Okay? Oh. It was all because of that asymptote question. That's how far it threw me off. When I'm grading exponential function graphs, right? And I'm coming up with, okay, how many points is this question worth? It's usually like, okay, 1 point for the asymptote, 2, 3 points for the, correct values of the points, and then a couple points for, whether it's connected correctly. Okay? All right. So asymptote is always takes precedence. You don't have to. Okay, let's do this one super quickly. Is this growth or decay? This is decay. So, okay. So for decay, all right. So let's pick -1, 0, 1 again. So you can also do -2, but so I quickly looked at this, and if this was -2, then it would have been 4 to the power of 2, which is 16, and it would be too big, right? So you kind of have a little bit of flexibility. Okay, so what's the horizontal asymptote here? Okay, y equals 3. So domain is all real numbers. What about the range? Okay, good. So -1 over 4 to the power of -1 plus 3. This is -4 plus 3 minus 1. So we're in Algebra 2 Honors. We're going to get those negatives correct. So -1 over 4 to the power of 0 plus 3 is 2. -1/4 to the 1 plus 3 is 2 3/4. So I just write 2 3/4 because that's easier to graph. than like, 11 over 4. Okay, let's do this. 3, 1, 2, 3. Asymptote goes first. -1, -1, 0, 2, and then 2 3/4. And so this is going to look like this. All right. Does this make sense? We said this was decay. Does it look like decay? As x approaches to the, as x approaches infinity, is the graph going towards the asymptote? Yes, that means it's decay. This is decaying to 0. Okay? All right. So, because there is a negative out here. This negative. Yeah? Okay, so take a look at this one. Growth or decay? Decay. What's the horizontal asymptote? Y equals 5. Domain is all reals. What is the range? Y is less than 5. Okay, so let me see here. All right, so let's do okay, so let's do -1, 0, 1. So -4, 1/2 to the what? -2 plus 5. This is -4 times 2 squared plus 5. So that's -11. Yeah? So this one here, this will be 2 to the 2. Right? Because it's a negative exponent. So -4 times 2 to the 2 plus 5. -4 times 4 is -16 plus 5 is 11. Okay. So -4, 1/2 to the 0 plus 5. This is -4 plus 5, 1. Oh, no. No. Sorry. This is -4 to the power of -1. Sorry. So then it's -4 times 2 plus 5, -3. Now this is -4 times 1/2 to the 0 plus 5. This is 1. All right. Asymptote is a 5. Y equals 5. -1, I'm at -11. Okay, that's fine. I'll just put that there. And then 0, -3. Yeah? 1, 1. Okay? Now, this is going to increase and go towards the asymptote. So make sure it goes towards the asymptote like that. All right? You got to curve it. Notice there are no like corners here, right? It's a smooth curve. It grows gradually but quickly. All right? Like smoothly but quickly. Okay, so let's do some word problems because what's math without word problems? All right. So let's talk about equations for exponential growth and decay. Exponential growth and decay, which increases or decreases by a fixed percentage, is usually modeled by these two equations. So for example, if like your rent increases by, this many, like 3% every year, if your salary increases by 3% every year, right? That's exponential growth and decay, growing or decaying by a fixed amount. Okay, so let's take a look here. A of t here, A of t is the final amount. Little a is the initial amount. Okay, rate is your rate in decimals, right? So divide the percentage by 100, and then t is time. So look, for growth, this is a plus. For decay, this is a minus. Yes, you have to memorize these. Okay? So, the decay factor and the growth factor are 1 minus r and 1 plus r. So, for example, if the rate is 3%, this will be written as 0.03. All right? So the decay factor will be 1 minus 0.3, and this will be 1 plus 0.3. Okay? Yeah. Huh? Yeah. Yeah. So let's take a look here. Okay, so take a look. Let's do some examples and you'll see what we are talking about. So the first US census was conducted in 1790. At that time, the population was, 3 million and so on. Since then, the US population has grown by approximately 2.03% annually. Okay? Classify the function representing the situation as either exponential growth or decay. So what do you guys think? Is this growth or decay? Growth. So this is exponential growth. Identify the growth or decay factor. So take a look. If this is 2.03%, you have to divide by 100, right? Move the decimal point to the left twice. So it's 0.0203 in decimal. So the growth factor is going to be 1 plus 0.0203. And then you don't leave it like that. It'll be 1.0203. Okay. Then write the equation and then graph the function on your calculator. Okay, so what's the equation going to be then? For the equation, we're going to use this format, right? So A of t, okay, is equal to the initial value, 3929214, times the growth rate, 1.0203, to the power of t. That entire thing is the equation. Okay? So, look at this. It says to write the equation. An equation, wait, let's wait to graph because this is important. An equation has to have two variables at least, an x and a y, right? So you have to label this A of t, blah, 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 to the power of t. That t in your equation has to remain as the variable t, right? So for instance, if somewhere else in the problem it's talking about like a span of 10 years, in the equation you can't put in 10 for that. Okay, so let's go ahead and graph this, please. We want to find the y-intercept and the asymptote and explain what those represent. Okay. So let's go to a graph. That's the initial amount. So 3,920,000. Oh, sorry, I need a graph. Okay, 3,929,214 times 1.0203 to the power of x. When you graph this, you don't see anything. Because what does A represent? It's the what of the US? Huh? It's the population. The population started at 3 million and now it's risen. So we got to be up there. Okay? Okay? Yeah, you have the window settings. So let's go to window settings. So I'm going to go up to what? So listen, what are we looking for here? We're looking for the y-intercept, right? The y-intercept at t equals 0. So, okay, so why don't we go up to 5 million and see how that looks? Okay, so I have a y-intercept there, okay? It's too small. Now, you can also, whoops, right? You can also like drag and zoom, okay? So take a look here. Okay, so let's find the y-intercept. The y-intercept is when x is 0, right? So if you do Control T, when x is 0, how much is the y-intercept? It's just the initial population, right? That's the y-intercept. Okay, so what is the y-intercept then? Is the initial population. It's always going to be the initial because the y-intercept is when this is 0, when t is 0. When t is 0, that's when the problem started, so it's the initial by definition. So what would the asymptote represent? Right, but what does the asymptote, so here is the asymptote, right? So in this graph, it would look like this. Here is the asymptote, and then here is the graph. So this is the initial population. What would the asymptote represent in terms of the population, huh? The smallest the population could possibly be or was, okay? So the asymptote represents the lowest population, right? So in this case, it would be y equals 0. Okay. All right. Next, a cup of green tea contains 35 milligrams of caffeine. The average teen can eliminate approximately 12.5% of the caffeine from their system per hour. Do you see how this is an exponential growth problem, or right? Because it's like every hour 12.5%, every hour 12.5%, fixed percentage, within an equal amount of time. Now, is this growth or decay? This is decay. So what is the decay factor? This is the percentage. So the decay factor, 1 minus what? 0.125. So that's 0.875. Write the equation, right? So if we wanted to write the equation, it's going to be A of t equals the initial amount. What's the initial amount? 35. And then 0.875 to the power of t. Do you see how this value is less than 1? It's between 0 and 1. So yeah, it's decay. Do you see how it all fits together? Right? So cool. All right, so here, we're going to get rid of the table, Control T. I'm going to do Doc B before I do anything because those windows were all sorts of crazy. So I'm going to graph 35 times, in parentheses, 0.875 to the power of x. Okay, nothing. But now, what would be, is 35 the minimum or the maximum now? It's the maximum because it's decaying, right? So let me go to my menu, window zoom, window settings. Let's go Y max to 35. Or you know what? Let's splurge. Let's go 40. All right. X min. So what does the x-axis represent? If the y-axis represents the amount of caffeine that's in your body now that you've had this tea, time. hours. All right. And we're not going to have negative 10 hours. That's just silly. So I'm just going to go negative 2 to give it a little bit of cushion so it looks pretty. So why don't we go like a span of 24 hours? What do you think? Let's do it. Oh my God, what a beautiful graph. Wow. That makes me so happy. Look at that. It tells the entire story of when you had the tea, and that's how much was in your body, and then it decayed. Is it ever going to be 0? No, right? Because the math, listen to me, this is important. The math says it's an exponential decay function, which means there is an asymptote, which means it will never go to 0. The math says so, and Mother Nature follows the math. It will never be 0 because then the equation would be wrong. You see that? You see that? Okay. So now that we graphed it, well, isn't that math though? Okay. Estimate the amount. Estimate the amount of caffeine in the teenager's body 3 hours after drinking a cup. So now take a look. This is A of 3. We're really gonna hone in on the notation this semester. A of 3. This is 35. Look, times 0.875 to the power of 3. Do you see that? So listen, you can either go to the home screen and just type that in, or you could go here, and if you do Control T, go to 3, and it's that many. So 23.44, how much? 22.447. Yes. It says to go to the nearest tenth. So 23.5 no, 23.4. Because it was 444. So it's 23.4 milligrams. All right, after 3 hours. Yeah. No, I said in the equation you cannot. This is where you were writing the equation, so you can't. Now that's the general equation. Now you're going to use that equation to find specific values. At that point, of course you can. Okay? But when you're asked to specifically write the equation, you got to have y and x in there.